Okay, so we're going to start moving on to what we call a normal curve. So this is another probability distribution. This one we have already calculated for us what the probabilities would be. So somebody had already went through and found the formula for this curve and has gone through and done the work of doing the calculus that we need to find all your particular areas. So what we're going to see here is we're going to use something called a Z table. And that Z table is set up by somebody already looking at a normal curve and figuring out all our probabilities. So a probability density curve, comes in several varieties. So we have all kinds of different kinds of curves. So depending on the characteristics of the population they represent. So some can be skewed, some can be bivariant, not bivariant, I'm sorry, can be bimodal, some of them can be uniform, some can be like that J distribution. So that one's like the first one we have is kind of like a J distribution. And then we can have these normal ones. So we've been talking about these bell-shaped curves all along. Many important statistical procedures can be carried out using only one type of probability distribution, which is called your normal curve. So there are a lot of things that are natural that follow the normal curve. So normal distributions have one mode, and the distributions are symmetric around the mode. So right here is my mode, middle of my whole distribution, right? So only one mode. So like I said, their mode is symmetric around the mode. Normal curves extend infinitely far in both directions. What that means is that this little tail here, it just keeps on going and going and going and going and going forever without ever actually crossing at zero. So this just keeps going along forever and ever. And it never crosses this line down here. Sometimes it looks like it does because it gets really small here, but what we know is happening is it's indefinitely that tail just keeps on going for infinity and it never stops. There's never a spot where it hits the x-axis and it quits. It just goes forever above the x-axis. Population mean determines the location of the peak, and the population standard deviation measures the spread of the population. Therefore, a normal curve can be wide and flat when the population standard deviation is very, very large. So an example right here. So this is my standard deviation. This one has a standard deviation of 1. This one is 2. So my standard normal curve is short and wide. Um, Also, if we have the opposite happens, it'll be tall and narrow when the population standard deviation is small. So this one has a smaller one, and then as we see, it's much taller. So they're supposed to represent the same amount of area. So it's like you're taking the same amount of area and you're just sort of like squishing things down. And if it squishes down, then it moves out. Or if you pull it out like this, then it has to get shorter. The mean and median of the normal distribution are both equal to the mode. So mean is going to equal median and is going to equal mode. With the mean, like I said, the standard deviation just tells you if it's going to be tall or short. Mean just kind of centers it. So wherever our mean is, it centers our whole distribution. These ones have the same standard deviation, but the mean changes where it is centered on the curve, or sorry, centered on the x-axis. The area under a normal curve, just like of all the other areas we've been looking at, represents a proportion of the population or can be interpreted as a probability. So probabilities and proportion are pretty much interchangeable when we're working on this. It is therefore necessary to find areas under the normal curve other than those specified by the empirical rule. So as of right now, only areas that we know how to find out under a standard normal or under our normal curve, sorry, are just areas that fit with our empirical rule. Like if I wanted to figure out this, like this is my A and this is my B, I have no idea how to figure out this area right now with any of the information that I currently have. but soon we're going to get that information. So if you remember, empirical rule followed if we had a normal distribution. Before we were saying a bell-shaped distribution. Well, that was a nice way of just saying it had a normal distribution. So according to empirical rule, when we have a normal distribution, remember when you're in this range where you're 1 standard deviation from the mean, that's where 68% of my data set. When I was 2 standard deviations from the mean, that's where 95% of my data sat. And when I was 3 standard deviations from the mean, originally we were saying it was all or almost all, but it's 99.7% of my data should fall in that area. So just kind of a recap on that. What we won't be able to do is know why is this 68%, this is 95, and this is 99.7. That's one of the things that we can learn in this section. But also, we want to be able to figure out something else. Like maybe the area I want to figure out is from here to here. I can't use empirical rule for that. That kind of gets making some connections here in a second. So the mean lifespan of dogs is 13.42 years with a standard deviation of 2.36. Assume lifespan of dogs have a normal distribution. We're going to use areas in the image to find the following. What is the probability that a dog lives for 8.69 to 15.77 years? So right here, this is taking your empirical rule, and these are all 1 standard deviation, 2 standard deviations, 3 standard deviations from the center of my data. So this from here to here, 1 standard deviation is 68%, so we just split it into half. So it's 68, we got 34 here, 34 here. If we did this area from here to here and added it all up, you should get 95. So it's still doing that empirical rule. The probability that a dog lives from 8.69 to 15.77 years, well, we get from here to here, from -2 to 1 standard deviation away is 13.5% of my data. Between 11.5 and 13.42 is 34% of my data. And then between 13.42 and 15.77 is another 34% of my data. So we're going to end up with 4, 5, 6, 7, 8, 9, 10, 11, 6, 7, 8. If we add that up, we're going to get 81.5% of dogs that have a lifespan somewhere between 8.69 and 15.77 years. What is the probability that a dog lives more than 20.49 years? Another thing to look at here is the standard deviation. So I tell me out of here. And this is 99.7% of my data, which means that we have a 0.3% left over. And if you remember, these tails here keep on going indefinitely. So there is still a little bit of things that can be in there. And like I said, it's about 0.3% of whatever is left over from the distribution are in those little tails. If I split them in half, that means right here, that's 0.15. And here is another 0.15. If I want to figure out B, we need to know what was in those tails before I can even do that. So probability the dog lives for more than 20.49 years is going to be 0.15%. Remember, all this is already in percent. What's the probability that a dog lives at most 11.05 years? Well, we just keep having to add up these probabilities because this is all less than 11.05 years. So 0.15 plus 2.35 plus, wrong number, plus 13.5 So we'll have 5 there. I believe that is going to be 16%. We add that up. I'm just going to add that up quickly, just one more time to make sure I have it. Yeah, 16. There's a 16% chance there. Like I said, and that's just using those areas, but I'm figuring out these probabilities right now still using empirical rule. Okay. We're getting close to where we're going to actually find these probabilities. So first we're going to talk about converting a normal distribution to z-scores. So what we're going to use, like I said, as a z-table, we also going to use a TI-84 to help us calculate probabilities. But before we can use the z-table, we need to know how to do this standardized normal distribution. So a normal distribution can have any mean and any positive standard deviation. Any of them work. It will still be, as long as it's a normal curve, it could be any mean, any positive standard deviation. What we're going to do is make something called a standardized normal curve. So having a normal distribution with a mean of 0 and a standard deviation of 1 is what we call a standardized normal curve. So it'll look like this. I can take any normal curve or make any normal distribution into a standardized normal curve or normal distribution. So we tend to use curve and distribution interchangeably. You'll see that as we go through this. So we're going to talk about how can I make any kind of normal distribution look like a standardized normal distribution, meaning I can make it have a mean of 0 and a standard deviation of 1. And the question to that is we use z-scores. Recall that a z-score for a data value represents the number of standard deviations the data value is above or below the mean. If x is a value of your normal distribution with a mean of mu and a standard deviation of sigma, we can convert x into a z-score by a method known as standardization. So part of what the purpose of a z-score is, it's going to make these standardized scores for everything. So it's going to standardize everything into z-scores, or really what it's doing is it's going to standardize x into its from the mean. And it's doing it in standard deviations. So it's kind of where it gets the name of it's being standardized because it comes from that standard deviation. So what we're doing here is we're taking a distribution of x's and we convert all those x's into z-scores. And once we do that, that's what's considered the standardization. So it's converting x's to z-scores. So that's all we're kind of doing here is we're converting it to something that is standard. So no matter what my distribution is, whatever the mean or standard deviation, I can always standardize it to z-scores. This is a common thing that we do in a lot of fields, is we take things and we can standardize it to something else. So consider we have a woman whose height is 67 inches with a normal with a normal population that has a mean of 64 inches and a standard deviation of 3. So I know these keep changing, but this is just one example. If I figure out my z-score, it's going to be the 67 minus the 64 divided by 1 or divided by 3, which is going to give me 1. Oops, sorry. Look, something weird on my side. Wait a second, make sure it's sharing correctly. Um, what this means is that 67 is one standard deviation from the mean. And we can have lots of distributions. Well, that same thing will happen where all kinds of numbers will be one standard deviation from the mean. So the value of 67 from the normal population with a mean of 64 and a standard deviation of 3 corresponds to a z-score of 1 with a from a standard normal distribution. And in a standard normal distribution, the mean will be 0 and the standard deviation is going to be 1. So what we're seeing here is I'm taking the score here of 57, and this is everything in X values. So it's my normal data. And then what I do is I convert it to this, so it fits into a distribution of Z scores. So I'm taking X scores and turning them into Z scores. That means that the 64 here, I need my arrows, that's 64. That was the mean of my distribution that corresponds to a Z score of 1. And that 67 course, or sorry, 64 corresponds to Z score of 0. My 67 one standard deviation away, so it corresponds to a Z score of 1. So everything here is going to get converted into a Z score and be able to be mapped on this curve as well. Since the mean of the standard normal distribution is 0 and the mean has a Z score of 0, I can't get my tool here. Since the mean of the standard normal curve is 0, yes, the mean would also have a Z-score of 0. I was trying to read that and I was not processing it correctly. So those will end up going together. Points on the horizontal axis to the left of the mean, we're going to have negative Z-scores. So anything over here is negative. If we're on this side, then my Z-scores would be positive. So we already talked about that before, that when we found out the Z-scores, we were looking below the mean, Z-scores were negative. We looked above the mean, Z-scores were positive. Okay, so we're going to talk about looking at a Z-score and kind of doing some interpretation on it. So a compact fluorescent bulbs are more energy efficient than incandescent bulbs, but they take longer to reach full brightness. The time it takes for a compact fluorescent bulb to reach full brightness is normally distributed with a mean of 29.8 seconds and a standard deviation of 4.5 seconds. A randomly selected bulb takes 28 seconds to reach full brightness. We want to find and interpret the z-score for 28. So remember, z-score is my x minus my mean divided by my sigma. We are told here, so for my population of incandescent fluorescent, or sorry, my population of fluorescent bulb, the mean is going to be 29.8. The standard deviation is 4.5. And then we're asked about a randomly selected ball. So this is my randomly selected variable. That will be my x. X will be the 28. So my z-score for 28 is going to be 28 minus 29.8 divided by 4.5. So remember, when anytime you do z-scores, that top part needs to be in parentheses. Or you just do that subtraction first, and then you go back and then you divide. A second, I have to do that again because I got like a z-score of 40, which I'm pretty sure shouldn't happen. This would be negative 1.8 divided by 4.5. And what we get is a z-score. Down here, I got something in my way here. Is negative 0.4. So we know that because it's negative, a couple things we know is that this is fairly close to the mean. We know that 28 seconds is close to the mean, relatively close in terms of standard deviations and everything. It's relatively close to the mean. Because it's relatively close to zero. Relatively close to the mean. And we also know that it sits. So remember, if they're negative values, they're going to be left of the mean. So it sits left of the mean. So when we have probabilities that are close to zero, that means there's events that are going to be more probable. So one of the things this also tells me is that this is a little more probable, but we're going to actually put some numbers to these kind of things here in a minute. Okay. One more question, because this is going to kind of get to what we're doing here in a few seconds, unless you pause the video. Earlier, we saw that the probability that that we have a probability of 81.5% of dogs are going to live between 8.69 to 15.77 years. So, like I said, what we have is 81.5% of dogs live between these two spans. We want to know, what are the z-scores for these two numbers? Well, earlier we saw that we had a mean of 13.42, and we had a standard deviation, or you can just use the fact that I substitute the z-scores. Second, I've got to go back here for a second to figure out what my standard deviation was. I think there's a little typo somewhere in here. But it's approximately 2.35 is the standard deviation. So what is the z-score? Well, I don't actually have to do a bunch of work here, because the way this was set up is that this area here is supposed to be where 68% of my data sits. This goes out to -1 standard deviation, and this is 1 standard deviation. So that means that this right here, the z-score, for 15.77 is going to be 1. Like I said, and the whole reason that works is because it's 1 standard deviation from the mean, therefore its z-score would be 1. This is 2 standard deviations from the mean. And it's also less than the mean, so my z-score for 8.69 would actually be -2. So this means that the area 0.815 or 81.5% is between what two z-scores? Is between the z-scores of -2 and 1. So remember, this is representing a probability. So up here, what we have is that the probability that a dog lives between 8.69 to 15.77 years is going to be 0.815 or 81.5%. But another way we can talk about that same probability is in terms of z-scores, because we know that 8.69 is just a z-score of -2. And now my x's are all z-scores. And that 15.77 is just a z-score of 1. And that gives me the same probability. So what we like about z-scores is I can take something, any kind of distribution, with any kind of mean, any kind of standard deviation, as long as it's a normal distribution, and I can convert everything to z-scores. And there, we would like to convert to z-scores because z-tables give me all my information, but I have to use z-scores to get that information. We have a way to take x's, convert them into z's, so then we can use our z-tables here in the future. In the not too distant future, actually.